In this chapter, we're going to discuss the finite difference method. Let me start with a well-posed PDE, the Poisson equation minus Laplace u equals f on a domain omega, where omega is an appropriate domain, f has the appropriate regularity, and u is the unknown. As you know, we need to have boundary conditions, and we're going to use the Dirichlet boundary condition. As a matter of fact, the homogeneous Dirichlet boundary condition. I will impose u to be equal to 0 on the boundary. I could, of course, do the same thing in dimension 1, and that would be a very simple ODE minus u second equals f on the interval 0, 1, for instance, with, again, homogeneous Dirichlet boundary condition, u of 0 equals 0 and u of 1 equals 0. Now, I could add to it, say, for instance, I could add a function c, so that would be minus u second plus cu equals f, with c being a function, a continuous function, from 0, 1 to r plus. Well, these are just examples of well-posed PDEs. We discussed these PDEs and ODEs before. What we did in the previous chapter, in chapter 5, is we approximated the solutions to these equations by using the finite element method, the FEM. And roughly speaking, the finite element method is simply meshing the domain omega, or the interval 0, 1. So we have a mesh. On this mesh, we build a finite dimensional subspace of elementary functions. For instance, hat functions. That's in dimension 1. I remember these hat functions. Or in dimension 2, we gave another example that was that were pyramids on these elements. So basically what we're doing is we have a subspace of elementary functions, and we project our unknown function u on this subspace of function. And of course, because we have a finite number of functions, we're going to have a finite number of coordinates of u on these functions. This means that what we have to solve is an equation that will provide us only with a finite number of unknown. Now, that will eventually lead to a linear system. So that is what we did with the finite element method to approximate the solution to a PDE. But there would have been another way. You probably remember that the derivative can be approximated by the Newton quotient. F prime of x is the limit when h goes to 0 of f of x plus h minus f of x divided by h. Or if you prefer, I can write it this way with the Landau notation: f prime of x equals this quotient plus small o of 1. Of course, that is provided that f is differentiable at point x. By the way, if I have more regularity on f, I can actually write things this way with the Landau notation big O of h, which is a little bit better than the small o of 1. Now, if you're not familiar with the Landau notations, I believe you are, but if you are not for some reason, I suggest you review the Landau notations, as they're going to be used extensively in this chapter. They already were in the previous chapters, especially when we did numerical methods in chapter 1. But again, if you're not familiar with these notations, then I strongly suggest you get up to speed with this notation, with the Landau notations. Okay, of course, now that we have the first derivative, we can iterate this process, and we can obtain the higher order derivatives, and we can approximate these higher order derivatives in the same way. Now, the finite difference method is going to be a method that will basically rely on these ingredients. First, we will mesh the domain that we are going on which the PDE is posed. If it is an ODE in dimension 1, then what we will do is just a subdivision of the interval. If it is in dimension 2, then we'll just mesh that domain, or in higher dimension, we'll also mesh that domain. And that is obviously the first step, the first ingredient of our finite difference method. Then we will approximate the derivatives, first derivative, maybe second derivatives, whatever derivatives we have to whatever order with the values of the function on the grid. Exactly using this type of quotients, this is what we're going to do. So we're going to replace the derivatives that appear on the PDE by quotients, where we're going to have things like this. And by doing this, the unknowns become the unknowns at on the grid. So we're going to have a finite number of unknowns, which means that we are coming from a problem where we have to look for a solution which is defined everywhere, to going into a problem where we have a finite number of unknowns, again, the values of u on the grid, and that will lead to a linear system. So somehow the beginning and the end are the same. We start meshing and we end with we end up with a linear system, but you can see that in between it's slightly different. So this is what we're going to describe in this chapter. Let me tell you how this chapter is organized. We are currently in the introduction, after which we will talk about the finite difference method in dimension 1. So we'll start with dimension 1 to understand completely what is going on. The first video we'll see in that section will be approximating the derivative. Then the second video will be approximating the higher order derivatives, after which we will see how we can put all of this together to approximate the solution of a PDE. And we'll choose as an example the PDE that we described before, minus u second plus cu equals f with homogeneous directed boundary conditions on an interval because it's dimension 1. And then we will see how we can actually obtain convergence of the method, and we'll actually put everything together, run a program, and hopefully get the approximation of the solution to our PDE, which will be again an ODE since that's dimension 1. In the second section of this chapter, we will investigate the finite difference method in higher dimensions, in dimension d greater than 1. And we'll start with meshing. That will be the first video of this section. Then we will see how we can approximate the partial derivatives. And finally, we will approximate the solution of a PDE, mainly minus Laplace u equals f with a homogeneous directed boundary condition. And the last section of this chapter will be section 3, that will be the comparison of the finite element method with the finite difference method. That section will be very short.